Welcome to Lecture 5, Natural Forcing Factors. So in this lecture, we will be discussing some forcings that affect climate. Those are mechanisms that can cause our climate to change that are natural, okay, not anthropogenic or human-induced. So we want to look at ways that the climate can change, drivers of changing climate that are not from humans. So the reading for this lecture is chapter 3 of Bloom, pages 45 through 54. So you will remember this figure from the first lecture. It shows CO2 concentration here on the top, going back 400,000 years before 1950. And it shows temperature change from the present being 1950, so yes, that's 66 years ago, in degrees Celsius. So it's very apparent that there's a correlation between CO2 concentration and temperature change, right? When CO2 concentration is high, relatively high, near 300 parts per million, temperature is warmer than present being 1950, 66 years ago. When CO2 concentration is relatively low, below 200 parts per million, temperature could maybe 7, 8, even 9 degrees Celsius cooler than 1950. Now, the two don't exactly, they're not carbon copies of each other, okay? There's definitely the strong correlation, but there are more wobbles in temperature, okay? A more noisy signal than for CO2 concentration. Nonetheless, a very apparent correlation between them. Now, the reason that I show this is to illustrate that temperature has changed before humans were present, okay? You'll remember that humans in our current form, Homo sapiens, have only been around about 200 to 250,000 years. And so if we go back to the left of 250,000 years ago, here, this is temperature changing before humans were even around. And temperature could fluctuate anywhere before even humans existed. Temperature could be a few Celsius warmer. It could be 7, 8 Celsius colder than what it was in 1950. Okay, so there's a very large range, and we want to understand how can that happen, right? Because we've been talking about global warming being driven by increases in greenhouse gas concentrations, and that's driven by a large, tremendous increase in greenhouse gas emissions since in the past 100 to 150 years. Even particularly even in just the past 50 years or so. And we would like to understand natural forms of climate change, okay? Natural ways to change the climate, okay? Drivers that can affect climate that are not from humans. And now looking at a more recent illustration of how temperatures varied. This is going back 18,000 years before the present. And again, like the previous figure, as you go to the left, you're going back in time. So you see this little upward spike here at the end. That's the present-day global warming, okay? That's the present-day global warming showing up on this figure going back 18,000 years. But there's been large changes in temperature prior to the current global warming being driven by increases in greenhouse gas concentrations, okay? In particular, increases in anthropogenic greenhouse gas concentrations due to humans. And you'll notice here during the Holocene maximum, which peaked around 5,000 years ago, temperature was warmer than the present. Now the present here, the thing is, the present is actually not quite now. So when you see temperature change, that's actually temperature change relative to the mid 1900s or so. Okay, maybe later 1900s. That's why you see at the end of the figure, temperature is a little warmer than it was before. But nonetheless, this Holocene maximum was a warm period. It's sometimes called the medieval warm period, and it was very relevant for civilizations. In fact, the first sophisticated human civilizations, such as those in China and Egypt, actually developed during the Holocene maximum. Okay, they started developing around 6,000 years ago. Most likely because the relative warmth of this era allowed for the systematic cultivation of crops and the creation of towns and cities. Okay, and then going back further in time, we see the noticeable rapid spike in temperature. Okay, it looks rapid, and then the drop off again, and the drop off wasn't a constant drop off. So this figure starts at the end of the last ice age, about 18,000 years ago, also called the last glacial maximum. And temperature slowly began warming, and then it began warming a lot faster as we got to about 14,000 to 13,000 years ago, and was almost what it was in the 20th century. Here, at this time, the Boling-Olaroid period, probably mispronouncing that, and then temperature dropped. And it would go up a little bit, and it would often drop a little more. And then it dropped a lot more about 11,000 years ago until we had another cool period called the Younger Dryas period. So we'd like to understand the reasons for these variations in temperature, okay? This is before the present-day global warming, way before it. What can cause climate to change that's not being driven by humans? So, when we talk about natural climate change, we can talk about a couple drivers of it, or a couple forcing factors. Okay, so a forcing factor on climate is basically a mechanism that can cause climate to change. So it's a driver of a change in climate. And there's two forcing factors we can discuss. The first is called an external forcing factor. External forcing factor. Well, what do you think external means? In a way, it means outside. So an external forcing factor is one in which the agent of change is outside of the Earth's atmosphere system. Okay? So that means that the driver that causes climate to change, temperature go up or down, and then of course there's other responses to changing temperature as well. Well, it's not inside the Earth atmosphere system. So it's not on Earth, it's not inside the atmosphere, it's basically in space, if you will. It's outside our planet, right? So it's something from outside the Earth that will cause climate to change. And we'll be discussing the examples of external forcing factors. You may already be thinking of some. The other form of a forcing factor that can drive changes in climate naturally is an internal forcing factor. And as you may infer, for an internal forcing factor, the agent of change is within the Earth atmosphere system itself. So unlike for an external forcing factor, in which the driver that causes climate to change is outside the Earth atmosphere system, for the internal forcing factor, it's inside the Earth atmosphere system. So an internal forcing factor is something that originates either on Earth or in the atmosphere that causes the planet's climate to change. Now, there are 3 examples of external forcing factors we will be discussing. And this would be a good opportunity to pause and try to come up with 3. So the first external forcing factor we'll be discussing is variations in solar output. Basically changes in the amount of radiation emitted by the sun. The sun does not always emit the exact same amount of radiation. Sometimes it emits more, sometimes less. Second, we have orbital variations. Those are changes in the exact ways that the Earth orbits around the sun. And so the Earth revolves around the sun once every 365.24 days. And over time, it's the way it orbits around the sun. And also, you have to also remember that as it's revolving around the sun, it's rotating on its axis. So also, as it's rotating on its axis, it's also slowly revolving around the sun. I say that because, of course, one rotation on the axis is 24 hours. That's only one day. So that's one rotation on the axis is going to be a very slow amount of time in terms of revolution around the sun. Nonetheless, as there are changes in how the Earth rotates on its axis, those also would compose orbital variations. And the third external forcing factor is meteors or asteroids. So I'm not an astronomer by any means, but from my understanding, meteors are bodies of solid or liquid material, usually solid, and they could be rocks, okay? And they're outside of the Earth's atmosphere system. When a meteor enters the atmosphere, it becomes a meteoroid, and if it makes it all the way to the ground without burning up, and it reaches the surface, it's called a meteorite, okay? And you've probably heard of meteor showers. An asteroid is a larger meteor, if you will, okay? So we're more concerned with, say, an asteroid impact than just a meteor impact, okay? Not to say meteors impacts can't do significant damage, okay? Especially the larger they are, the greater the area of the crater, and the bigger the deal, okay, in general terms. Now, let's talk about internal forcing factors briefly, and then again we'll be going into more detail about each of these factors. Can you think of any internal forcing factors? Try to come up with 3. Again, what on Earth or in the atmosphere can cause climate to change that's not driven by humans? Remember, we're talking about natural forcing factors, mechanisms that cause the planet's surface temperature to change over time that are not caused by us humans. 1, volcanoes, right? When a volcano erupts, it can emit smoke, ash, dust into the atmosphere. And we'll be talking about it can also emit carbon dioxide into the atmosphere, and that affects climate. Plate tectonics is another one. This one isn't completely intuitive, but it turns out, as you may remember from studying some form of geology, either in high school or college, the Earth's crust is made of plates, and these plates are constantly moving, and slowly, but they're moving. And they're moving past one another, they're sliding under one another, they're sliding over one another. And boundaries between plates are called faults, and plate tectonics refers to basically the movement of plates. And this has formed the continents as they are today. We'll be talking about it, but hundreds of millions of years ago, there was a supercontinent and called Pangaea, and slowly over time, the continents spread apart to make the world map that we know today. But also, you may know about plate tectonics in the sense that when the plates move violently enough, that can cause earthquakes. So here in the Bay Area, we are along the San Andreas Fault, which divides the North American Plate and Pacific Plate, and they're actually sliding in opposite directions relative to one another. And because of that, in millions to millions of years, LA will be basically in San Francisco's backyard. But by that time, there might have been so many earthquakes and who knows what else that, we might not be here, right? Who knows what the world's going to be like then. Then we have one other, changes in atmospheric composition. Now we know about how anthropogenic changes in atmospheric composition have caused climate to change, but we're not the only thing. Us humans aren't the only thing that can cause the composition of the atmosphere to change. Okay, for example, remember going back 400, even 800,000 years, CO2 concentration would fluctuate, and before the 20th century, CO2 concentration was never above 30 parts per million. Nonetheless, it would vary between 180 and 300 parts per million. And that's long before humans were around, okay? So there's other ways besides us emitting CO2 to cause it to go up. And there's ways to take it out of the atmosphere and remove more than is being let in, which would cause CO2 concentrations to go down. So we'll be talking about these in detail. Let's start up with solar variations. And one example of a solar variation is a sunspot. Okay, sunspots correlate with solar activity. The more sunspots, the more energy emitted by the sun. And radiation is, again, one of the three methods of energy transfer. And we can think of solar energy or solar radiation kind of in the same with the same mindset. So, solar energy, solar radiation, we're talking about the same thing, output from the sun. So, may have heard of sunspots. Here is figure 3.15 from the book, and there's a couple pictures from telescopes. On the left, the larger figure shows the sun and what it looked like on March 29th, 2001, 15 years ago. And it shows sunspots that were present. These black dots here, there is this cluster of them in this region, but there are a few on other parts of the sun's surface as well. Those are sunspots. Okay, they look like darker areas of the surface of the sun. Right, most of the sun's surface looks a orange color, but these sunspots are darker. And this figure on the right is basically zooming in on one of those sunspots. And the sunspots are very large, okay? Sure, they look small with respect to the sun's surface area, but you have to remember how huge the sun is, right? It's so massive. So in some of these sunspots are actually basically the size of planets. This was a planet-sized sunspot. So the sunspots actually have cores that can extend thousands of kilometers long. So, what causes sunspots? Okay, you might be wondering why the sun will sometimes have these spots covering it. And one thing that you'll learn, or you might know already, is that sometimes sunspot activity is higher, other times it's lower. We're going to be talking about the solar cycle, which refers to the cycle of sunspots. Now, sunspots are caused by periodic changes, okay, but in the alignment between the sun's rotational axis and the gravitational center of the solar system. Okay? So read that carefully. Sunspots are caused by periodic changes in the alignment between the sun's rotational axis, the axis on which it rotates. The sun also rotates, but the planets revolve around the sun while the sun rotates at the center of the solar system. And the gravitational center of the solar system. So since the sun is at the center of the solar system and it's so massive, you might think it should be the center of gravity in the solar system, and it generally is. But the axis on which the sun rotates and the true gravitational center of the solar system, they don't always line up exactly in the same position. And when alignment changes over time, that can actually produce sunspots because it produces intense fluctuations in the magnetic field of the sun. And when the magnetic activity is high, sunspot activity is high. Now, sunspots have temperatures of about 3,500 to 4,500 Kelvin, which is 5,840 to 7,640 degrees Fahrenheit, okay? Tremendously hot. You have to remember how hot the sun is. The surface is, and it gets hotter as you go into its interior. But the surrounding regions of sunspots have temperatures of 5,500 Kelvin or 9,440 degrees Fahrenheit, okay? So now you might be wondering, well, wait, if sunspot activity is high, why is there more solar energy? Because remember how we said that when there's more sunspots, basically the sun emits more radiation. Because sunspots are clearly cooler than the rest of the sun. And the reason that the sunspots appear darker is due to lower intensity of radiation emitted. The reason they look darker is because the regions of the sun covered by these sunspots are cooler and they emit less radiation upward. So you might think that when sunspot activity is high, the solar energy reaching Earth should be less, but the opposite is true. What happens is heightened solar magnetic field activity that produces sunspots increases the overall brightness of the sun, and that more than compensates for the dark areas within the sunspots. So sunspots might only make up maybe a few percent of the sun's total surface area. And what happens is when the magnetic activity of the sun is higher and there's more sunspots, the rest of the sun gets brighter, and the overwhelming majority of the sun, 97, 98, 99% of the surface area perhaps, okay, so the overwhelming majority of the surface area gets brighter. And so even though there's more sunspots now, there's more cooler areas of the sun, the rest of the sun gets brighter, it gets warmer, it emits more radiation, and that more than compensates for the cooler areas of the sun emitting less radiation. So as a whole, the sun emits more radiation. Now there's a cycle that is clear. Here we are looking at some telescope photographs of the sun in the early to mid 90s. And then we have this graph showing sunspot number on the vertical axis with respect to year. And yellow is showing yearly running mean, basically yearly running averages of sunspot number. In green are 27-day running mean, or basically monthly running averages. So the yearly running averages basically smooth out the data. Regardless of the whether you look at the monthly running average or the yearly running average, there's a clear trend, okay? Sunspot activity increases and decreases on a consistent basis, okay? So here we are looking at 5 different relative maximums in sunspot activity, 5 peaks of the solar cycle. We have one here in the late 1940s, another one in the late 1950s, another one around the turn of the 60s and 70s, another one in the early 80s, and another one in the early 90s. So you see that there's a little more than about a 10-year, maybe 11-year, okay, if you're looking at this for the first time, I'll tell you specifically soon, but a little more than a decade cycle, in the sense that every 11 years there's a maximum in sunspot activity, okay? So if you're at one of these peaks, it's going to be at 11 years before you're at another peak. Conversely, if you're at one of these minimums, it's called a solar minimum, where there's no sunspots, about 11 years after that, the sun will again have no sunspots. Now, not all solar cycles are the same strength. Some are stronger than others. So out of these 5, this one looks the highest, okay? Strongest. This one occurred in the late 50s, and there were as many as 250 individual sunspots covering the sun. By the way, the sunspots can last anywhere from a few hours to a few months. Okay. So this solar maximum, okay, was significantly weaker than the others. Here, there were maybe only 100, 150 sunspots covering the sun, and that was perhaps as low as half of this sun's solar maximum. So not all solar maximums are as strong. Now we can look more recently, zoom in on more recently what's been going on with solar activity. Here we have solar cycle sunspot number from January 2000 to near present, January 2016. And we had a solar maximum in the early 2000s, around the turn of the millennia, right? Remember the Y2K bug when year 2000 happened? And there were up to 175 or so sunspots. And then you see how activity declines. And in the late 2000s, around 2000, as we got into late 2008 into early 2009, we reached a minimum, and then the activity began picking up again. And we just recently, about a couple of years ago, reached a solar maximum, and now activity is declining again. And it should continue to decline until around 2020 or so, and then it'll reach a minimum and then pick up again. Okay. By the way, ISES stands for International Space Environment Service. All right. So some key points about the solar cycle I'd like you to understand. Sunspot numbers increase and decrease. Okay, we've seen this. They go up and down, and they go up and down over an 11-year cycle. So the cycle is 11 years long. The solar cycle has been observed for centuries. In fact, Chinese astronomers recorded the presence of sunspots as early as 28 BC. But systematic counts and more accurate counts of sunspots began with the invention of the optical telescope. And Hans Lippershey, a Dutch lens maker, is usually credited for the invention of the telescope in 1608. Okay, but there were astronomers, there were other ways to detect solar activity before that. And the counts with the telescope show that the number of sunspots varies with, again, 11-year period, as well as some with less predictable longer cycles. By the way, sunspot numbers can be reconstructed from tree rings. Sunspot activity reflects the strength of solar magnetic fluxes that divert cosmic rays from striking Earth. And when cosmic rays collide with nitrogen atoms, that generates carbon 14 that can react with oxygen to produce radioactive carbon dioxide, and trees can incorporate this carbon dioxide. So sunspot numbers are inversely proportional to the carbon-14 levels in trees. So if you're looking at tree rings, you can actually use that to help figure out sunspot numbers. Now, individual spots last from a few hours to a few months, and studies show that the sun is in fact about 0.1% brighter when solar activity is high. So it's not a lot, but it's a detectable amount. When the solar activity is high, the sun's about 0.1% brighter than average. And when solar activity is low, when there are no sunspots, when we're at a solar minimum, the sun's about 0.1% dimmer than average. Okay. Now, even though there's a clear 11-year cycle in sunspot activity, there have been some exceptions to the more common trends. Here is figure 3.16 from your book, and we're looking at number of sunspots going back to the early 1600s. Okay, so basically looking at near 1600 to present, and again the telescope was invented in the early 1600s. Okay, so basically looking at sunspots number as long as we've had telescopes, which have enabled more accurate representations of the number of sunspots. Okay, the sunspots were known about. Astronomers knew about them prior to the invention of the telescope, but it was hard to count exactly how many sunspots there were before the telescope was invented. And by the way, you might be wondering, well, what makes a sunspot, a sunspot? There's certain criteria that it has to meet, I think, in size and in order for it to be classified as a sunspot. Okay, you saw that the sunspots might be clustered together. Are there two sunspots, or are they combined, or is that one sunspot? I'm sure NASA has their ways of characterizing them, which if you were interested in, you could look into. Anyhow, here we're looking at sunspot number again for a 400-year period between 1600 and 2000 or so. 1 year average is in green, 11-year average is in red. Longer average is a way of smoothing out the data. And you'll see that, again, some sunspot solar maximums are stronger than others. Okay, here was one. The one that we saw from the 50s when there were 200 plus sunspots on the sun. That was very strong. Okay, that one was, it looks like from this data, the strongest going back 400 years. Okay, it looks like from this data that it's quite uncommon for there to be more than 175 sunspots on the sun. Now, again, this is 1 year average. You have to remember that, but nonetheless, this definitely stands out as a very strong, perhaps the strongest. And then there were some weaker ones, weaker solar maximums, late 1800s, early 1900s. Some of these solar maximums might only have 50 to 75, 100 sunspots. Now, one clear exception to the normal trend is this time period. Focus your attention here. Between the mid 1600s and early 1700s, when it looks like no sunspots. Okay, there was an absence of sunspot activity. And this is called the Maunder minimum. The Maunder minimum was an absence of sunspots that was well observed, and it lasted from 1645 through 1715. So this was a 7-decade event, or this was a period of time that lasted 7 decades. Okay, would you consider that a lifetime on average, right? And so usually every 11 years, there's a maximum in solar activity, but here was a time for 7 decades there were no sunspots, and this so-called Maunder minimum coincided with a cool climatic period in Europe and North America known as the Little Ice Age. So this is a clear clear what's the word I'm looking for? Clear representation of a possible connection between the sun and climate. We see that when there were no sunspots, and we know that means the sun was dimmer, the sun wasn't as bright, it was emitting less radiation, Earth was cooler, okay? And so we shouldn't be surprised that the Maunder minimum coincided with a cool climatic period in Europe, and especially Western Europe and North America. And there were bitterly cold winters in Europe and North America, crops died, okay? This had a big effect on society and civilizations, and this was again known as the Little Ice Age. It wasn't a real ice age, but it was a very cold period, and so it was called the Little Ice Age because it was shorter than a normal ice age, and it wasn't as dramatic, but it was a definitely noticeable cool period with climate period with effects. And this was not an entirely unique occurrence in the sense that it has happened before. Okay, it has happened before. So notice that there is a clear 11-year cycle usually, but there are exceptions to that. All right, now what was the second external forcing factor that we mentioned? It was orbital changes. So we're going to be discussing orbital changes next. Now, these orbital changes are often called Milankovitch theory, and Milankovitch is the scientist who proposed them. Okay, so he's a very important figure when we talk about orbital changes because he put forth three different orbital variations that can affect climate. Okay, so he's a Serbian astrophysicist, and during the 1920s, he studied the effects of solar radiation on the irregularity of ice ages. And he didn't look so much at sunspots and variations in the actual output of the sun and how that affected the irregularity of ice ages, but how orbital variations of Earth as it revolves around the sun can affect the ice ages, cause or end or begin ice ages, how they can cause climate to change, because he found that there were three orbital changes that could actually impact the amount of radiation taken in. So even if the sun doesn't change in strength, regardless, not looking at sunspots, not looking at variations in solar activity, there are three orbital variations that can actually affect how much sunlight is taken in by a certain place on Earth, say over the course of a year. So the variations in Earth's orbit that he proposed were the following. 1. Changes in shape of the Earth's orbit around the sun. You may know that the Earth does not revolve around the sun in a circle. It revolves around the Earth in an ellipse. It's almost a circle, but it's a slight ellipse. And how elliptical the orbit is changes. Sometimes it's more elliptical, sometimes it's more circular. We call changes in the shape of the Earth's orbit around the sun eccentricity. And that has a period of 100,000 years. So what that means is if the Earth's orbit around the sun is as circular as it gets, then about 50,000 years later it'll be as elliptical as it gets, and then another 50,000 years after that, 100,000 years after the initial time when it was as circular as it gets, it'll be as circular as it gets again. So think back to how there's the solar cycle period of 11 years. So it takes that long to go between maximums or minimums. It would take half that time to go from a maximum to a minimum. The second variation in Earth's orbit that Milankovitch proposed was wobbling of the Earth's axis of rotation. So, as the Earth rotates on its axis, it slowly wobbles like a spinning top. And we're not talking about changes in the tilt of the axis. We're talking about it wobbling in 360 degrees slowly over time. And so one thing you'll notice about these orbital changes is that they're very slow, or you'll begin to notice, or you're noticing. You saw that with changes in the shape of the Earth's orbit around the sun. It takes a long time for the orbit to go from more circular to more elliptical. But the same is true for the other variations. So the wobbling of the Earth's axis of rotation has a period of 21,000 years. So it takes 21,000 years to completely spin on its spin, basically wobble on its axis, one complete circle. And we call the wobbling of the Earth's axis of rotation precession. Now the third variation in the Earth's orbit that Milankovitch proposed is changes in the tilt of Earth's axis. Remember how from lecture 4 when we were talking about the seasons, we were talking about the Earth is tilted on its axis at 23.5 degrees, okay? And that's with respect to a perpendicular line through the plane of its orbit around the sun. Well, that tilt changes, okay? Sometimes the Earth is a little more tilted on its axis. Other times it's less tilted. And the changes in the tilt of Earth's axis is known as obliquity. And that has a period of 41,000 years. Okay. So these processes are involving the Earth's orbit around the sun that can affect climate. They're very slow. You're not going to see the effects of them in your lifetime. Okay. You're not going to see the Earth's axis tilt change in your lifetime. You're not going to see that affect climate. You're not going to see Earth becoming more elliptical, and that would actually increase the distances, the variation in distance between the Earth and the Sun over the course of a year. You're not going to see that really impact your life, but through ice core data, we can reconstruct temperatures going back long periods of time, and we can find evidence for these orbital variations that Milankovitch proposed. So, quick question for you. If the Earth's tilt was to decrease, how would the summer temperature change at our latitude? Okay, so if the Earth's tilt was to decrease, it's at 23.5 degrees now. Let's say if it was less and the Earth wasn't as tilted on its axis, how would that affect the summer temperature at our latitude of San Jose? And San Jose's latitude is about 37 to 38 degrees north latitude. We're in the mid-latitudes. Would our summer temperatures increase? Okay, number one. Would the temperatures in the summer decrease? Would it be cooler? Would summer temperatures stay the same? Or do we have no idea, or not that we have no idea, that is it impossible to tell from this information alone? So think about that, come up with a choice, and then come back to the video. A decrease in the tilt would cause a cooler summer at San Jose at our latitude. Why? Well, because if Earth's tilt was to decrease, the seasonality of the planet would decrease. Remember, the reason that we have seasons in the first place is because the Earth is tilted on its axis. And if the Earth was not tilted on its axis at all, okay, we'd basically have spring and fall all year round. There wouldn't be much variation, okay? There'd be a little variation in temperature over the course of a year because of the changing distance to the sun, but the temperatures over the course of the year would be pretty consistent. And so the less the tilt, as tilt decreases, the seasonality is going to become less, so summers become cooler and winters become warmer. Okay. Conversely, if Earth's tilt was to increase, how would the summer temperature change at our latitude? Well, it would become warmer because we'd have even greater seasonality, warmer summers and colder winters. Now, as we said, the Earth orbits the Sun in an ellipse. Okay, so here's a diagram showing that orbit around the Sun in an ellipse with some terminology that you already know some of it, and some good terminology to know. We have perihelion. You'll remember that's basically the point in orbit when the Earth is closest to the Sun, and that occurs January 2nd through 5th. Okay, in northern hemisphere winter. Placed in orbit closest to the Sun. And aphelion, on the other hand, is the point in orbit where Earth is farthest from the Sun, and that occurs July 3rd through 6th, most years July 4th, during the northern hemisphere summer. So what you see is the ellipse that Earth orbits around the Sun, and what you see is that the Sun, shown by this yellow blob here, is not at the center of the ellipse. It's at what's called a focus. Okay, you might remember foci, the plural focus from algebra, high school algebra 2, I think, when you were talking about equations for ellipses. And since the Sun is at one of these foci, what that helps you see is how the distance between the Earth and the Sun changes over the course of a year. Now, by the way, this figure is greatly exaggerated. Okay, it's greatly exaggerated, but still, it's true in the sense that the Sun is not quite at the center; it's at the foci of the ellipse, and the distance between the Sun and the Earth varies over the course of a year. Okay, here is figure 310 from your book, and here's the Sun at the center of the orbit, and the Earth's orbit around the Sun changes. Black is a more circular orbit, whereas white is a more elliptical orbit. Now, precession. What's precession? That's the wobbling of Earth on its axis like a spinning top. Okay? In the period, it's about 21,000 years. Now, Here's Earth. Here's it tilted on its axis, okay, and it rotates once every 24 hours. And what precession is going to do is it's going to change the times of perihelion and aphelion. Okay, it changes the times of year when they occur. So it takes Earth 21,000 years to complete one full circular wobble on its axis. Okay, the analogy would be it takes 21,000 years for the top to complete one full wobble circle. And that means that 10,500 years from now, the times of aphelion and perihelion are going to be reversed from what they are now. So now here's the sun, and this is even more exaggerated, right? It looks like in northern hemisphere wintertime, perihelion, it looks like the sun is maybe a third of the distance between than what it is in summertime aphelion. But the reason that it's exaggerated is to help you try to see the changing distance of the sun. Anyhow, in 10,500 years, once the Earth has completed one half wobble on its axis, now in northern hemisphere summertime, okay, July 3rd through 6th, that's when perihelion will be. So now perihelion is going to occur July 3rd through 6th in northern hemisphere summer, and in northern hemisphere winter between January 2nd through 5th, when perihelion occurs. Now that's when aphelion will occur. So you'll be celebrating aphelion along with New Year's, as opposed to today when you're celebrating aphelion along with the 4th of July, Independence Day. Okay. Now this could affect the seasons, right? The strength of the seasons, because think about it now. In 10,500 years from now, in the summertime in northern hemisphere, not only the days are going to be longer, the sun's high in the sky, but also the Earth is closer to the sun. Okay, and now in the northern hemisphere wintertime, not only will the days be shorter, the sun will be lower in the sky, but the sun will also be farther from the Earth. Okay, the Earth will be at this farthest point in the orbit from the sun. So now the effects of solar angle, basically, and daylight length will be in phase with changing distance of the sun. So you may expect stronger summers and weaker winters in the northern hemisphere from this alone, precession, not talking about changes in the ellipsity of Earth's orbit around the sun, or changes in the tilt. One thing that you have to understand is that these three orbital variations are constantly happening. Okay, it's not like one will happen over 21,000 years and another one will happen over 100,000 years. They're separate. They're constantly the variations are happening together. Okay. So here's 2006 AD near now. And you've seen this figure before. It shows how it's really nice to understand the seasons, but as you see, the Earth is tilted on its axis, and you see how the northern hemisphere is facing or tilted toward the sun on June 21st, away from the sun on December 21st. And right now, and this is exaggerated again, the distance that the sun is exaggerated, but you see how now in northern hemisphere winter, when the northern hemisphere is tilted toward from the sun, away from the sun, the Earth is closer to the sun, and in the northern hemisphere summer, when the northern hemisphere is tilted toward the sun, okay, the Earth is farther from the sun. Well, 10,500 years ago, if you subtract 10,500 years from 2006, it's not a simple subtraction. I mean, well, actually, in a way it is, because if you do 2006 minus 10,500, you'll get negative 8,494. And that means negative 8,494 means 8,494 years before 0 AD. Okay? And at that time, when the northern hemisphere was experiencing summer, the Earth was closest to the sun, and when the northern hemisphere was experiencing winter time, the southern hemisphere was experiencing summertime, the Earth was farther from the sun. Farthest. Okay? And if you like, you can see some larger figures, larger blown up halves of that previous figure, if you will. Now, here's figure 3.8 in the book, and this is a nice figure because it's illustrating two, actually, of the orbital variations. It says obliquity, but it's also illustrating precession. So the Earth, you might be wondering, well, how tilted on its axis can Earth be? Okay, we're talking about how the Earth's tilt on its axis changes. It could be more or less than 23.5 degrees, but how much? Okay, 45 degrees, 30 degrees. It's not that great of a variation, but it has a substantial impact on climate nonetheless. So at greatest tilt, the Earth is at an angle of 24.5 degrees with respect to a perpendicular line through the plane of the orbit around the Sun. And at the other extreme, the Earth's tilt on its axis is only 22.1 degrees. Okay, so it varies. But what you also see here is precession, the spinning of Earth on its axis. Okay, I've kind of been describing this as Earth, but this is a top. This, of course, looks like a top. And the reason for this figure is to illustrate how Earth wobbles on its axis like a top, to help you understand what precession is, how it looks, and also how the tilt changes. Obliquity, of course, happens, and that could happen because, if you have this spinning top, it also might change its tilt. Now, this figure 3.9 has a lot of great information on it. It's titled Influence of Orbital Variations on Solar Insolation and Historical Temperature Changes of the Orbit. Okay, so let's first focus on the left part of the figure. We have three different variables, if you will, dependent variables. The independent variable is time. Okay, so on the x-axis we have year, a million years ago. And what we're looking at is obliquity, eccentricity, and precession with respect to time going back 2 million years. Okay, so this 0.4 million years would be going back 400,000 years. Okay, that CO2 concentration, temperature from the ice core data figure we've looked at. This is going back 800,000 years, and so on. And we can look at the relative magnitudes of these three orbital variations. So starting with obliquity, remember how that's variations or changes in the tilt of Earth's axis, or Earth on its axis. Okay. So you see the values for obliquity are in degrees, and the values range from about just over 22 to about 24.5 degrees, and that's what we said earlier. Okay, so the tilt, it's going to be anywhere from 22.1 to 24.5 degrees. And if you wanted to see the average tilt, okay, you drew a line, try to find the average over the time period. It's about 23.5 degrees, what we know to be true. Sometime, and just like okay, for the solar maximum, some solar maximums are stronger and some solar minimums are weaker or stronger. Okay, remember how not all solar cycles have the same strength. Well, not all periods of high obliquity and low obliquity, not all variations in the tilt between a minimum tilt and a maximum tilt are as strong. Okay, so sometimes there's not much variation over the course of 21,000 years. Okay, as other times. Excuse me, 41,000 years. Okay, 41,000 years. That's actually good to transition to this part of the figure. This is showing frequency. Okay, it shows events per mega year or per millions of years. And if you know the events per millions of years, you can figure out the relative frequency of a maximum or a minimum, and that gives you the period. So here, this is we have a clear period of 41,000 years. Okay, for eccentricity, okay, that's basically changes in how elliptical the Earth's orbit around the sun is. That varies from about near 0 to 0.05, okay, maybe a little greater. And when the eccentricity here is 0, that means that basically the Earth's orbit around the sun, it's circular. It's basically circular. And when it's 0.05, it's as elliptical as it gets. The pattern for eccentricity over the last couple million years, it's a little more complicated. There's actually a few peaks here, but if you do it, you try to find the majority of the frequencies. You try to find what really stands out. It's about 100,000 year period. Finally, we have precession, wobbling of the Earth on its axis. Now, precession has a couple dominant frequencies that appear that come out of the data. One at 23,000 years and one at 19,000 years. And so that's where the 21,000 years number comes from for precession. All right, now, can we see any evidence of these orbital variations on climate? Well, if we go back to the temperature change figure from going back 400,000 years from the Vostok ice core data, and you'll remember how it's correlated with CO2 concentration. Look at the minimums in temperature. Okay, so the ice ages, the end of the ice ages. Hey, remember how I told you the last ice age ended about 18,000 years ago or so? Well, 50,000, 40,000, 30,000, 20,000. Here it is. Here's the end of the last ice age, everyone. Now, the end of the... So basically, where you see these rapid upward spikes in temperature, those are when the ice age ends and we go to a warm period. So here's one. Okay, this one not as quick of a spike, but here's another one. Here's another one. We'll look at what period of time they're separated by. So here's the end of the end of an ice age about 340,000 years ago or so. Okay, and CO2 concentration was relatively low, near 200 parts per million. And then the end of the next ice age, well, it was about 240,000 years ago, and that's about 100,000 years separation, right? And then if you go to the end of the next ice age, okay, when the next ice age ended, it was about 140,000 years ago. Okay, so you see that these periods in which the temperature rapidly spikes when the ice age ends and it warms up, the ice melts and the sea level rises and gets warmer, those periods are separated by about 100,000 years, okay, and so on. And so we'll remember what we were talking about, okay? Remember how eccentricity has a period of 100,000 years, okay? So this could be possibly a clue of the ellipsity of the orbit affecting the ice ages. Okay, let's move on to talk about glaciers and how they form. We can discuss how orbital variations could play a role in glacier formation. So, what are glaciers? They're basically composed of fallen snow that's compressed into a large, thickened mass of ice over many years. All right, so when the snow gets compressed, goes under a lot of pressure, it turns into ice, and when this body of ice gets large and thick over many years, it becomes a glacier. By the way, glaciers are different than ice sheets. They move faster. There's a couple major types of glaciers. There's alpine or mountain glaciers, and there's the higher latitude glaciers. Now they're large, but They are faster moving than the ice sheets that cover Antarctica and Greenland. Now, when do they grow? Or what years do they grow and what years do they decay? Okay. Well, glaciers usually grow when yearly snowfall in winter is greater than snow melt. So when there is more snowfall in the winter than the amount of snow that melts in the summer, the glacier grows. And this should make sense, right? Because if there's more snowfall in the wintertime than there is snow melt in the summertime, you're going to add more snow. There's a net addition of snow over the year. Conversely, when yearly snowfall in wintertime is less than snow melt in summertime, okay? So when there's actually more snow melting than in the summer than had fallen the previous winter, the glacier decays. And this should make sense because there's a decrease in snow over the course of the year. So keep these glacier growth and decay points in mind as we continue. Here's what a glacier looks like. Here's the Perito Moreno Glacier in Argentina. Very beautiful. Okay. And by the way, we'll be talking more about this in the future. But one thing that's happened with global warming is the glaciers are disappearing. Okay. There's not as many of them as there used to be. They're becoming smaller. The ones that would be in the mountains, they used to go down to lower elevations, but they're receding back to the higher parts of the mountain. They're decreasing in area. So another thing about glacier decay, it's basically a net removal of glacier area. Okay, it's sometimes called glacier receding. Okay, so here's a connection. There is a connection between summer sunshine and ice volume. Okay, so now we're looking back 600,000 years ago. As we go down the diagram, we're going back in time, and we're looking at summer sunshine on the x-axis. One thing that stands out when you look at this figure is that when summer sunshine is high, more insolation in the summertime, and that could be a result of a change in the tilt. That could be a result of the change in the ellipticity of the orbit. That could be a change in the times of precession and aphelion because of precession. Okay, that could be an effect of multiple of these orbital variations together. But when there's more insolation in the summertime, there's lower ice volume. Okay, and the reason is because when there's higher summer sunshine, stronger seasonal strength, if that could coincide with stronger seasonal strength, stronger summer, there's more snow melt. Okay. And conversely, when you see some of these relative minimums of summer sunshine, less sunshine in the summer, okay, perhaps a cooler summer, more ice volume, okay? So let's talk more about glaciers and seasonal strength. So Milankovitch not only was studying the effects of the orbital variations on the irregularity of ice ages, he was also figuring out how seasonal strength affects glacier growth and decay. So he proposed that when solar insolation in the northern hemisphere was relatively high during December and January, so that's warmer winter time, right? And so he's talking about northern hemisphere in particular. But he put forth if the solar insolation in the northern hemisphere was relatively high during December and January, warmer winter time, okay, and relatively low during June and July, colder summer. So warmer winter, colder summer, that would be a weaker season, right? More snow accumulated during the winter and less melted during the summer, causing glaciers to advance. Okay. So this might not be completely intuitive to you. because you might be seeing, okay, well, if the seasonality is weaker, let's say the seasons are weaker and strained, so it's cool. This could happen when the Earth's axis tilt is less. Okay, let's say the Earth's axis tilt is less. So we have a cooler summer and warmer winter. Well, you might say, I get why it's cooler in the summer, so less of the snow will melt. Okay, but why should more snow accumulate in the winter? Well, he actually found that, and this is true, that when the reverse was true, if it's colder in the winter, actually, if it gets too cold, as it becomes colder and colder, actually, the snowfall decreases, because the colder it is, the less moisture the air can hold. So in fact, one thing that's true about Alaska is that the coldest parts of Alaska, okay, far northern Alaska, and also the Antarctica, and this applies to Antarctica, the Arctic, they're very dry, okay? Because when it gets extremely cold, there's just not much moisture at all in the air, so there's not much moisture for precipitation. So what can be seen is that when the seasonality is weaker, the axis of the Earth's axis tilt is less. It's cooler in the summer, warmer in the wintertime. That would promote less snow melt in the summer, more snowfall in the wintertime, and hence glacier advance. Okay, advancement. Here's the reverse, though. Okay, here's the reverse. Let's say that the seasons were stronger. The Earth was more tilted on its axis, okay? More tilted on its axis, so then it was colder in the winter, warmer in the summer. If it's colder in the winter, it's going to be drier, okay? And it's not as much snow, it turns out. It's going to be too cold. And warmer in the summer, then it's going to, there's going to be more snow melt. So more snow melt, less snowfall, and glacier retreat. Okay. Here's an activity. Here is an activity for you to do, and you'll be working on this in the discussion forum. So consider the fact that today, the perihelion of the Earth's orbit around the Sun occurs in the Northern Hemisphere winter, right? Perihelion occurs between January 2nd through 5th in the Northern Hemisphere winter. And in 10,500 years, the perihelion will occur during Northern Hemisphere summer. Okay. So, in 10,500 years, perihelion will actually occur July 3rd through 6th. Now, what I want you to do is explain how the climate, specifically temperatures in winter and summer of the Northern Hemisphere, would change in 10,500 years. So that would be what? 12,516 AD? How the temperatures in winter and summertime here in the Northern Hemisphere would change in that 10,500 years just due to precession, okay? So don't worry about any of the other orbital variations right now, okay? Don't worry about obliquity, don't worry about eccentricity. Just looking at precession, looking at how in 10,500 years, perihelion is going to occur in Northern Hemisphere summer, and hence aphelion would occur in Northern Hemisphere winter. How are the temperatures in winter and the summer? Will they change? Okay, so is it going to be colder in the winter and summer? Is it going to be colder in the winter winter and warmer in the summer? Is it going to be warmer in the winter and colder in the summer? Or is it going to be warmer in both the winter and summer? Okay. So answer how the temperatures for both winter and summer will change in the Northern Hemisphere 10,500 years from now because of precession alone. Then the second part, B, of this activity is how would that affect the presence of Northern Hemisphere glaciers? Grow, decay, or stay constant? And also you'll want to explain your reasoning, so that will be assigned in the discussion to explain your reasoning for your answer for B. Okay, moving along. Here's a quick note about eccentricity and how it plays a role on the effects of perihelion and aphelion on seasonality. So when Earth's orbit around the Sun is more elliptical, when eccentricity is higher, the effects of perihelion and aphelion on seasonality are higher. So if the Earth's orbit around the sun is more circular, perihelion and aphelion will still have an effect on seasonality, how strong the seasons are, but not as great as if the Earth's orbit is more elliptical. So the more elliptical Earth's orbit around the sun, the greater the effects of perihelion and aphelion on seasonal strength. Okay. Internal forcing factors. Now we will be discussing these internal forcing factors in detail. So what were they again? Volcanoes, plate tectonics, and changes in atmospheric composition. Let's start with volcanoes. So, check this picture out. This is a figure showing the eruption of Mount Pinatubo in the Philippines between June 12th through 15th of 1991, before most of you were probably born. Okay. So Mount Pinatubo erupted in the Philippines in June of 1991 after over 4 centuries of inactivity. And it spewed vast amounts of sulfur dioxide and fine particles into the atmosphere. So in the fine particles included smoke, dust. Okay, you can kind of see this looks like a large cloud of perhaps dust and maybe smoke, maybe ash combined. Okay. And these materials quickly spread over most of the world, and it formed a haze of aerosols in the upper atmosphere that reflected sunlight to lower global temperatures by about 0.2 Celsius for nearly 2 years. Okay, you were asked about that for your first homework assignment. Okay, and volcanic eruptions as large as Pinatubo occur only every century or so, but smaller yet significant eruptions, such as Mount St. Helens in 1980, in Portland, Oregon's backyard, El Chicon, they occur every decade. Now, these volcanic eruptions can emit aerosols in the atmosphere and cool the planet, but all eruptions also release carbon dioxide, okay? A greenhouse gas that contributes to global warming. The amount of carbon dioxide released from volcanoes, though, averages about 10,000-fold, okay, 10,000-fold less than that from modern-day burning of fossil fuels. Therefore, on balance, volcanic eruptions cool rather than warm the planet. Okay, so you might be wondering, do they cool or warm the planet? Overall, they tend to cool the planet, because even though they can emit CO2 into the atmosphere, in fact, they all do, that CO2 is very little. It's a tiny fraction of how much CO2 is being emitted from fossil fuel burning for power generation, for transportation, for manufacturing, okay, and so on. And so their cooling effect, their albedo effect, tends to dominate over their greenhouse effect, okay? And so we were talking about the Little Ice Age earlier, but the Little Ice Age did last for a few hundred years, okay? There was a peak in the Little Ice Age around the period of the Maunder Minimum, but some historians and some scientists consider the Little Ice Age to have began in the 1400s, and in the 1400s there were a lot of volcanic eruptions that could have helped trigger it. Okay. Plate tectonics. We were talking about Pangaea, okay? About 250 million years ago or so, all the continents were clustered together, and even 135 million years ago during the Jurassic period, you notice the continents were still much closer together than today, and the oceans hadn't formed to their current capacity. 135 million years ago, North America and South America were not yet connected. South America and Africa fit together. Okay, India moved a lot. It was like an island. Okay, Australia was somewhat connected to Antarctica, and over time the continents moved further apart, and the modern day oceans formed. You might be wondering, well, how can this affect climate? Right? This is geology, right? We're talking about Earlier we were talking about plates and plate boundaries and faults and quakes. Okay, you're wondering, well, that's in the earth, right? How does that affect climate? Well, there's some ways, okay? Orogeny, Orogeny, is the process in which tectonic movements of Earth's crust or volcanic activities form mountains, okay? So sometimes when the plate tectonics form mountains, and mountains, especially those with a north to south orientation. Examples: the Sierra Nevada in California, the Rocky Mountains in Colorado and Wyoming, the Appalachian Mountains in eastern U.S., the Andes. Well, they disrupt global atmospheric circulation patterns that generally move east to west because of Earth's rotation, okay? When the air runs into the mountain, the mountains can force it to move in other directions. An uplifting of mountains also exposes rock that undergoes chemical weathering and absorbs CO2. So when mountains get uplifted, that can expose rock underneath that can absorb carbon dioxide during chemical weathering and remove it from the atmosphere, which affects climate. Moreover, mountains tend to accumulate ice and snow that increases Earth's albedo. Okay, so when mountains form and they're building and becoming taller, that'll form new areas of snow and ice and increase albedo of Earth, which of course affects climate. For these reasons, times of relatively rapid mountain building, say from about 40 million years ago, when the Himalayas and Sierra Nevada first arose, until today, as these ranges continue to uplift, are usually cooler periods. All right. Last internal forcing factor is changes in atmospheric composition, and you've seen it. You can go back, but you can look back at the figure showing CO2 concentration varying over 400,000, even 800,000 years if you go back to the one figure from the first lecture. And obviously humans haven't always existed. There are other processes, natural processes, that put CO2 into the atmosphere and remove it from the atmosphere that we've talked about. Okay? Photosynthesis, respiration, volcanic eruptions, okay, to name a few, right? And this lecture is on natural forcing factors, but one apparent change in atmospheric composition that we can see is the changes in atmospheric carbon dioxide in the recent decades because of humans. And this is, of course, the Keeling curve, right? CO2 concentrations keep going up, but there is the annual cycle due to plant photosynthesis and respiration where CO2 concentrations peak in May of the year, and then they reach a yearly minimum in September or October, where we talk about that more detail in the carbon cycle in a couple of lectures. Okay. Of course, CO2 concentrations now are above 400 parts per million. So that wraps up Lecture 5 on natural forcing factors. Okay. I realize we went into a lot more detail about the external forcing factors compared to the internal. The book does go into more detail about the external forcing factors, but hopefully you got a good understanding of the internal forcing factors. You saw how they impact climate. Some of them we've talked about before, and we'll be talking about again in the future.